was asked, is this going to be a math-intensive chapter because it has the name geometry in the title? No, it's not actually. You're going to have to memorize maybe 4 or 5 different shapes and know them. You're not going to have to work them. You're not going to have to do any proofs. There's no corollaries and theorems and those kind of things. So you may be disappointed or you may be excited about that, but we're going to be dealing with polyatomic ions and molecular geometries. What does it mean when a molecule has a particular geometry, and how does that affect how it reacts with other molecules? Start off with a discussion on polyatomic ions. And we went over this in class about this word polyatomic. What does it mean if something is polyatomic? Has multiple atoms. Multiple atoms that together make an ion. It's not one ion, not one atom that makes an ion, but multiple atoms that make an ion. Polyatomic ions are ions that form when a group of atoms gains or loses an electron. We said before that an ion, for example, sodium and chlorine, when we make sodium chloride, we're making salt. That sodium here is the metal. It has 1 valence electron, and chlorine has 7 valence electrons. And so we talked about ionic compounds before. Those ionic compounds were formed when an ion is formed, when something loses and something gains an electron. In this case, what does sodium want to do? It wants to lose an electron, and chlorine wants to gain one. So we say, hey, we can work something out here. Why don't I just donate my electron to you, chlorine? And sodium becomes, at that point, a positive charged ion. It becomes a cation. When sodium donates its electron, it gives it away. It no longer lays claim to it. Gives it away, it becomes a positive. Chlorine receives the negative electron, and so it now has a net charge of negative. And when you have a positive and a negative, those two charges attract one another, right? They're going to come together. And that's how we form an ionic compound, an ionic bond. That ionic compound is formed when the positive and the negative ions are attracted to one another because of their opposite charges. This is all reviewed from the last module. But it's the concept behind polyatomic ions and how they work too. We're going to discover that polyatomic ions form compounds in the same way with these ionic bonds, where they have a charge, so they're an ion, and they form a compound with another ion. We'll talk about one you're going to see all the time. This is the hydroxide ion. Hydroxide ion is made up with a hydrogen and an oxygen. Hydrogen has 1 valence electrons, and normally we would draw that in the 3 o'clock position, but because I'm going to form this compound in this way, I'm going to place my available address, my available location, towards the other element, towards the other, what's going to become an ion. So let's orient towards the chemical we're going to bond with. You see that there's 1 valence electron. It wants to have how many? 2. It's one of our exceptions. Hydrogen wants to have 2 valence electrons, and oxygen has 6. And again, I've oriented it so at least 1 open address is towards that place where I know I'm going to form a bond. Now, what kind of a bond is going to be formed between an oxygen and a hydrogen atom? Ionic or covalent? Okay, because they're both nonmetals. So we would anticipate that there would be a covalent bond between those 2 atoms. Nothing new here, right? It's pretty straightforward. What's the charge now of that molecule? If I rewrite it just a little bit, we've got 6 and 7 protons, right? 6 and 7, so there's 7 total protons. 1, 2, 3, 4, 5, 6, 7 total electrons. Right now, there's no charge, positive or negative, it's neutral, right? But look at what happens here. Oxygen still is vacant 1 address. So oxygen is trying to fill that 1 vacant address. See, oxygen doesn't have its octet yet, does it? Okay, how many does oxygen see? When oxygen is doing its electron count, how many electrons does it see that belongs to it? 1, 2, 3, 4, 5, 6, 7. And so while it's neutral, there's still that striving to have that valence shell complete. Oxygen is looking for an electron to complete its valence. That empty address right there needs something to fill it. So what would happen if a sodium atom were in the area and has its one valence electron? Sodium is still trying to get rid of that one, correct? Rather than receive 7, it's going to try to get rid of 1. Oxygen still has one available address. Even though it's a neutral charge at present, it still can receive one more to complete its octet. And so when sodium, in that case, donates its electron to the hydroxide, it now forms a net negative. Remember before we looked at sodium and chlorine, chlorine had one available address and it received the sodium ion. The same thing, or excuse me, the sodium electron. The same thing is happening here. Rather than it being one element though, it's a combination of the OH compound. This compound is lacking one electron to complete the valence. As opposed to just oxygen, for example, looking for 2. Oxygen is sharing an electron with hydrogen, so now it's only looking for one more. And it can form that by receiving the electron from the sodium, making a sodium cation and a hydroxide ion. And in much the same way, because sodium now has a positive charge, and the hydroxide ion has a negative charge, that they're bound together to form an ionic bond for the compound sodium hydroxide. Okay? So you understand the principle there. First of all, we started again with sodium chloride, NaCl, from last chapter. And so pretty obvious, donated electron becomes positively charged. The receiving atom becomes a negative ion. The two of them are attracted because of opposite charges. In this case, we've got an element and a molecule, and the molecule is looking for one additional electron. And so it receives the one electron, forming a positive ion for sodium, making itself negative. Once this molecule is now complete, if we look at oxygen, now it's considering itself to have 1, 2, 3, 4, 5, 6, 7, 8 electrons. And hydrogen has 2 electrons, 1, 2. So both valence, the octet rule is satisfied for both of those. But together, they have one more electron than they have protons. Remember, they have 6, 7 protons, and yet we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. One more electron than protons, giving this ion the -1 charge. Conceptually, any questions? Again, concept, positives and negatives attract each other. Pretty straightforward, right? Sodium and chlorine would attract each other. The sodium cation and the chlorine anion would attract one another because of opposite charges. Here, if you look at this and just consider this as you would the chlorine ion with a negative charge, it would be attracted to a positive charge. The negative charge here comes from the donation of the electron from sodium. I've abbreviated this PAI for polyatomic ion. So whatever the ion is, whatever the chemical makeup of this polyatomic ion is, let's say that it has a -1 charge. It could have 1 atom, 2 atoms, 3 atoms, 4 atoms, 5 atoms, 6 atoms. However many atoms it has, if we looked at the whole thing and discerned that it has a -1 charge, and we happen to have a metal in proximity, the metal's going to say, okay, I'm going to give you my electrons to complete you, and I'm going to take on a charge, you're going to take on a charge, and the two of us are going to be attracted to one another. Whatever the makeup is, We're going to look at a standard set that you're expected to know, to have memorized in just a moment. There may be a polyatomic ion that ends up with a net negative 2 or a 2 negative charge. If I told you before we're looking at the periodic table and we're looking at something like, sulfur. Sulfur is a column 6. It's looking to pick up 2 more. It's a 6A, so it's looking to pick up 2 more. It's looking to become 2 negative. And so if I have a metal in the area, let's say that it needs to come up with a equal but opposite charges, right? This is a 2 negative. It needs, if I gave it a 1 positive, it would still be looking for another 1 positive to balance it out, right? So those would combine together in combinations of 1s and 2s. And what we're going to find out is we're going to use the same shortcut to figure out the ionic molecules based on their charges. The same shortcut's going to work with the polyatomic ions as well. Now, matter of fact, of all the polyatomic ions that you're going to be expected to memorize, there's only one of them that's a positive. And that positive example is ammonium. Ammonium is an NH3 molecule that has a positive 1 charge. So this is the exception. All the other polyatomic ions you're going to learn are going to have negative charges except for ammonium, NH3. So because ammonium is going to have a positive charge, it's going to be looking for something with a negative charge to be attracted to bond with. Okay? The chart from your book, table 5.1 for those of you with module 5. What is it in module 2 for anybody that has it open? The table number. Page 288, table number 9.1. Okay. So 9.1 for second edition and 5.1 for third edition. Here's this table of polyatomic ions that, like it says in there, frankly, you just need to memorize it. Right now, I would encourage you to take flashcards and start building these flashcards up with the name on one side and the chemical formula on the other, and include the charge. The charge is going to be very important. Just start drilling yourself on them, because there's going to be quizzes on it. It's going to be on the test. Matter of fact, you just need to know this for the rest of chemistry. Just start drilling now on these ions in the same way that when we first had to memorize the 20 elements, remember? Seemed like a big deal now, but if I throw an S up there or a K up there, you know what the atom is. In the same way, we're going to be using the phrases chlorate and dichromate and cyanide, those kind of things in the future, and you need just to be able to write the formula down for it. But notice that every one of these has an associated charge given to it. Ammonium being the only one with a positive charge, everything else being negative, either -1, -2, or -3. See, chlorate, it's a -1, -1, so on. These are all -1 charges. This side over here, cyanide is -1, but then from here down, -2, -2, -2, -2, -2, and 3 for phosphate. So you can remember phosphate's the exception in that it has a -3. Ammonium's the exception in that it's a positive. There are a few other rules that you can learn that'll help you out a little bit here. For example, if the ion ends in the word ate or ite, because it has an oxygen in it. So if it has an oxygen in it, oxygen here, chlorate, oxygen here, chlorite, nitrate, nitrite, acetate, carbonate. So all of those with ates, they have an oxygen in them. And then when you pair these up, like here's chlorate and chlorite, nitrate and nitrite, sulfate and sulfite. When you have the pairs like that, whichever polyatomic ion has the greater number of oxygens, it has the ate name. For example, chlorate and chlorite. Chlorate, ClO3. Chlorite, ClO2. If you remember chlorate and chlorite are ClO, then it's down to which is which, ClO3 or ClO2. The greater number has the ate, and the lesser number of oxygens has the ite. Again, I don't necessarily need to copy all this down from the PowerPoint slide. This is in your book. But just remember that you do need to memorize this chart. And these are a couple, hints to help you get them right. We can. Let me see if we actually do one here. H. I've just got some people are copying this chart down, so I'm giving them a few moments more. Matter of fact, if you allow me, I'll go ahead and continue with this presentation, then we'll do that either at the end but we will do it. Okay.
Are those the only polyatomic ions?
They're just there are more. There's just the ones for this course. Okay, but remember what polyatomic ion means. It means that if you were to see on your paper a CrO4, you might try to start naming that, but it's not. It's a covalent molecule that's going to behave like a single ion. It's a combination of atoms to form a molecule, and yet that whole molecule takes on a charge. It's not any part of it. The charge doesn't come from the carbon, and it doesn't come from the oxygen in carbonate. It's not where it's coming from. It's coming from the combination between the two is still leaving us two available addresses to fill up the octets. That's why it has a -2 charge. Okay, because when it receives those 2 electrons to fill the octet, it then has 2 surplus electrons. And has a -2 charge. When we're naming compounds that use polyatomic ions, we're going to use the same naming paradigm that we used before. Remember, I encouraged you, for example, with sodium chloride, that it's named sodium chloride because the metal is going to lead and the non-metal is going to follow. So the sodium, in this case the metal, keeps its name and it leads. That's why it's not chlorine sodiumide, it's sodium chloride. So the metal leads and then the non-metal takes on its "ide" name. You can think of it this way. The electron donor leads, and the electron receiver follows with a modified name. Okay? Isn't that basically what we did? The electron donor leads, the electron receiver follows, the lead keeps its name, the follow gets a modified name. It's not sodium chlorine, it's sodium chloride. In the same way, when we name ionic compounds that use polyatomic ions, we're going to be doing the same thing. The positive ion is going to lead, the electron donor is going to lead, the electron receiver is going to follow with a modified name. So in this case, potassium chlorate, we have a potassium ion forming a bond with a chlorate ion to make potassium chlorate. Potassium is the electron donor, so it becomes positive, so it leads in the name. Chlorate is an electron receiver, and so it trails with its polyatomic name. Potassium chlorate. Questions on that? In this part, we've drilled like crazy last module. Should make sense. So using that same naming paradigm. That's why you wouldn't have a chlorate potassiumide or something like that. The metal leads. In this case, the electron donor leads. The electron receiver follows. Everybody have that? I saw some notes being taken still. Yes. Yes, they're covalent molecules that have a net charge. Okay. So, questions like these, and this is example 5.1. It's the first example in probably both textbooks, if not similar to this. What's the chemical formula for calcium nitrate? Well, first step, going to go ahead and identify the ions that make up the chemical formula that you're looking for. Calcium nitrate, made up of calcium and nitrogen, right? But we're going to identify the ions, then we're going to balance the charges, and finally write the formula. It looks exactly like we did last module when we formed ionic bonds between metals and nonmetals. Here we're going to do it between metals and a polyatomic ion, or ammonium and a nonmetal. So identify the ions. We're looking at calcium nitrate. Calcium, it's a column 2 element, so it's looking to become a positive 2. It's looking to give away 2 of its electrons. And nitrate, and looking at the table, you'll see that nitrate has a 1 negative charge. So in terms of the mechanics of what we're going to do now, we've done all of this before. The only thing that's new here is what is this molecule, how's it made up, and what is its charge? If I had said to you we're going to do a CaCl, calcium chloride, you would put calcium here, you'd put a chlorine here, and you would have said chlorine has a 1 negative charge. The chloride ion has a -1 charge. How do we know? It's a column 7A element. It wants to receive 1 electron. When it receives the 1 electron, it would become a -1. Okay? Now we're saying is rather than having a chlorine in there, becoming a chloride and looking to have a -1, we've got nitrate, which has a -1. So now we're going to balance the charges. If this were chlorine or chloride, 1 negative, what would we do to form calcium chloride? How would we do that shorthand-wise? Right, so if I had Ca and it wanted to become 2 positive, and chlorine that wanted to become a 1 negative, how would I get the formula for calcium chloride? I would take the superscripts, transpose them, and ignore the charges, right? And it would become CaCl2. We're going to do the same thing here with calcium and nitrate. Calcium wants to be a +2. Nitrate wants to be a 1 negative. Now here's a recommendation I have for you, is when you do this step, put your polyatomic ion in these parentheses. Putting them in the parentheses is going to keep you, or is going to ensure that you remember that this charge right here is being applied to this entire molecule. The entire NO2 molecule has that 1 negative charge. So that when we do the next step, which is to transpose, okay, that we remember that this is being applied to this whole thing. In this case, the 1 is going to be the subscript of all of calcium, and the 2 positive here is going to become the subscript of the entire NO2 molecule. So we do that. We just transpose them. And now we're going to ignore the charges and write the formula from left to right. See, I've ignored the negative, and I've also ignored the 1. Why? How can I just ignore the 1? 1 is implied. If it weren't a 1, if it were 0, it wouldn't be there. There would be no calcium. Its very presence means that there's at least one of them. If there's more than one of them, we tell how many by putting the subscript. So calcium nitrate, the entire nitrate polyatomic ion, we need to have 2 of them. And so if I ask you right now, how many calciums are in this molecule? There's 1. Good. There's 1 calcium in this molecule. How many nitrogens are in that molecule? How many nitrogens? Okay, there are 2 of them. There's 1 nitrogen for every nitrate, and I have 2 nitrates. So I have 2 sets of 1, or 2 nitrogens. How many oxygens do I have? Right, there are 4 oxygens. Why? Because for every 1 nitrate, I have 2, and I have 2 sets of 2 to give me 4. So there's 1 calcium, 2 nitrogens, and 2 sets of 2, or 4 oxygens in that molecule, calcium nitrate. I know this one is in the book, but don't look at the answer right there. And just right now, you can use the table, because you haven't memorized those yet. Let's go ahead and try this one as if it was on your own. What's the chemical formula for magnesium phosphate? Okay. Magnesium phosphate. We're going to identify the ions, balance the charges, and then write the formula. So go ahead, just in your notes, just go ahead and give it a shot. What would be the formula for magnesium phosphate? I'd highly encourage you, if you're not doing well, to give this a shot, okay? I see some of you I know that are trying, but you're struggling in the class as a whole, but you're not trying this one right now. So please, give it a shot. What are the ions that we're going to be looking at? Well, for magnesium phosphate, obviously if there's magnesium involved, right? Magnesium phosphate. And magnesium is a column 2A element. The valence are at the 1, 2, 3 S2. So we have a 3s2 valence. It wants to lose 2 rather than gain 6. Bless you. So magnesium is looking to become a positive 2, or 2 positive. Phosphate from the chart is a PO4 molecule. So the phosphorus and the oxygen form that molecule by using covalent bonds. And it has a net charge of 3 negative. So what's the combination going to look like when we balance the charges? I'm going to rewrite it and put my entire phosphate molecule in parentheses and put the charge outside of that so I make sure I keep it straight. Now that I've written it that way, I'm just going to transpose my superscripts as subscripts and ignore the signs. So the 2 is going to go underneath the phosphate, and the 3 is going to come over to the magnesium. And then I'm going to rewrite the formula, ignoring the signs. Mg3, quantity PO4, 2. Make sure you feel comfortable what this formula is saying. It's important for you to be able to identify how many of each element are in this molecule now. So let's just walk through it real quickly. How many magnesium atoms are in this compound? 3. There's 3 magnesiums. That's straightforward because it's Mg3. The 3 tells me I've got 3 of the element that's before the subscript. So I have 3 magnesiums. Now I'm looking at the molecule for phosphate, PO4. I've got 2 of them. 2 sets of whatever is inside the parentheses. 2 sets of PO4. right? So how many phosphorus do I have? 2 of them. There's 1 per molecule, and I have 2 molecules. So it's 2 times 1, or 2. How many oxygens do I have? 8. Because I have 4 per, and I have 2 of them. 4 times 2 is 8. So again, it's pretty straightforward. If you have, in this case, you have a single element, how many do you have? You have as many as the subscript. If there's no subscript, you have 1. Over here on this entire molecule, how many do you have? You take the subscript of the individual molecule, the element within the individual molecule, and multiply it by the subscript of the entire molecule. How many phosphorus? I have 1 times 2, or 2. How many oxygens? I have 4 times 2, or 8. Because you will see questions that say, in this molecule, how many oxygen atoms are present, or how many oxygens are used to form this molecule. If we were to decompose this, remember decomposition is to take a compound and break it down into its constituent elements. If we were to take this and break it down, we could forecast, okay, if I have 1 million of these molecules, how many oxygen atoms should I end up with when it's completely decomposed? Well, if I have 1 million of these, I should end up with 8 million oxygens. But for right now, just looking at that, you should be able to identify how many of each element are in that compound. Any questions on that? On how to figure out how many magnesiums, how many potassiums, or how many oxygens are in this molecule? It's always written that way if there's more than one of them. In fact, I think the next example, there's only 1, and so you'll see it now without the parentheses. So what is the chemical formula for copper 1 acetate? Okay, what are the ions, the balancing, and then the formula? So what are the ions that we're looking at here for copper 1 acetate? Well, obviously the first one's copper, right? And what's the charge of that copper going to be? Right, copper is not one of our A column elements, right? It's not 1A, 2A, 3A, 4A. It's a transition metal. And so for the transition metals, we need a little bit more information because copper can form multiple ions. In this case, we know that it's going to have a 1 positive charge. It's a metal, so it wants to be an electron donor. It's going to donate 1 because we've been told it's copper 1. Whatever's in the Roman numeral indicates how many electrons it's going to give away. So in this case, copper 1, copper is going to give away 1, and when it gives away the 1, it's going to become 1 positive. The copper 1 is going to bond with what kind of an other molecule? The acetate molecule. Acetate is C2H3O2. So this is 1 copper ion, and then acetate has a charge of 1 negative. So this carbon, hydrogens, and oxygens, these 1, 2, 3, 4, 5, 6, 7, these 7 atoms are in a covalent relationship with one another, and together, all together, they have a net -1 charge. So now we go to balancing the charges, and you would go ahead and rewrite it. You could go ahead and rewrite it and put parentheses around here. As a matter of fact, if you want to always put parentheses around it, I would encourage you to do it all the time rather than to forget to do it when you need it, okay? But here's what we're going to see. Because there's a +1 charge here, I know that when I do my transposing, that I'm only going to have one of these molecules. And so maybe I thought a little bit ahead. You know, we could have the parentheses here. And as I said, I would rather you put the parentheses in all the time than forget to put them in one time when you need it. So if you wrote it that way, that's probably a better way as you learn this to do it. But just as before, we're going to go ahead and transpose the numbers, and we're going to ignore the signs. And because they're both going to be 1s, we can ignore them because it's implied, right? So the formula looks like that. CuC2H3O2, copper acetate, copper 1 acetate. Because in here I have the acetate polyatomic ion. Now, parentheses are used so that as you look at the compound, you can get clues onto the construction. We had this once before. We had a molecule that had a hydrogen in it, and it had some other elements, and then it ended with OH. And it looked kind of odd, because at that point we'd never seen an element show up more than one time. I don't remember exactly what that molecule was, but I do remember explaining to you, saying, okay, don't worry about it right now. When you count up how many hydrogens you have in this molecule, remember to count the first one and the last one. There's a hydrogen in there. There's also an OH in there. And at that point, I couldn't go because it's a polyatomic ion and they're bound together. But what that molecule did was tell you, hey, here's a clue on the actual construction of the molecule, because hydrogen showed up twice in the formula, but the second time it showed up, it was part of the OH molecule. Okay? And so it gives you a sign or gives you a hint to the construction when it shows up in that way. Whenever you have a polyatomic ion like this, or if we go back to the last example, if I see this with parentheses around the molecule in a formula, that gives me a hint to the way the thing is constructed. In other words, the building blocks that put this together, one building block was magnesium, another building block was this PO4 molecule that came as a set already. It's like a building block that's made up of other blocks. So as I'm bringing them together to make this molecule, I have the raw material of magnesium ions and the raw material of phosphate ions, and the phosphate ions were already constructed for me before they came in a particular way. And so I'm not starting with simply the most basic elements. Remember we said an atom is when you break it down and can't break it down any farther. Magnesium is that. You can't break magnesium down any farther and still have magnesium, right? An element. Here you can take phosphate and you could break it down into potassium and oxygens. You can decompose it even farther. So it's kind of a secondary construct. We build up the phosphate ions, and then we build up the magnesium phosphate molecules. Yes, sir?
I was going to ask if it'd be incorrect in the one that had the oxygen appear twice, if it'd be incorrect to like merge them together.
It would say it's not standard. And you're gonna pick up on the standard nature of that as we go through. Let me go back one. And again, maybe I'll look up one of those to give you an example. It's just because it's new to you now, and if at that point in your learning, let's say, for example, before when you didn't know that there was such a thing as a hydroxide ion and how the molecule is actually constructed. I mean, let's be honest. At one point in time, this was just all gibberish to you. You walked into class, you sat down, I don't have a clue what any of that means. Now, hopefully you're at least sitting here going, I got a clue what that means. I may not be great at it, but I got a clue at what it means. And they construct a molecule like this. That's why in the past we weren't asking you to construct the molecule if it might appear twice, the same symbol appear twice, because you only knew, hey, all this is showing me is how many of that, how many of this, and how many another. Well, actually now you're going to start seeing that the standard way of writing it actually gives you insight into this construction. So that when I go to draw the molecule, I have hints in the way that the standard form, the way it's written, will give me hints to make sure that my construction is accurate. Because when we move from polyatomic ions into geometries, how it's constructed is significant. It's not enough to simply have two of them. It's significant on where you place those two within the construct of the molecule, the way we diagram it. Okay.
Is it possible for two polyatomic ions to bond, and the one that had that positive charge could it bond with the one that had a negative?
Yes. Yes. Hear the question? Is it possible to have two polyatomics bond? Remember, once they're bonded together, once you have that molecule form and it has a charge, and you have another molecule form and it has a charge, now we're just looking at opposite charges attracting one another. So it's like pieces of magnet. You have positive pieces and negative pieces. Actually, you can't have pieces, but you know what I mean. The orientations. If you were able to have set charges in different locations, it doesn't care what's making it negative and what's making it positive. If it's opposite, it's going to be attracted to it. If it's the same, it's going to be repelled from it. Because we're no longer sharing, we're just either attracted to. Because remember, once those ions are formed, they're not giving or receiving anything. They're just attracted, and they're going to come up and bump next to each other. And those electromagnetic forces are going to hold them together. But they can be separated apart, again, by dissolving in water, for example, and separate the ions. Covalents don't dissolve in water. You can't just simply stop the sharing. I mean, once you start sharing, you've got to add more energy than that to break them up. Because they're invested in one another now, okay? Okay, they're invested. It's like a divorce. They don't want to go through that. It takes energy. It takes a lot of energy to break up that kind of a bond because there's a shared electron involved. And they're going to be something different when they lose that. In an ionic bond, they're just going to go back to being two ions. And they're going to find another opposite charge and pair up. So. Interested in spending the next 5 minutes in starting a walk into geometries? I mean, this is the polyatomics. Okay, the no means we definitely have to. Right? Huh? Yeah, okay. See, you want to. So, okay. See, there's no right answer, because if you say no, that means we better. If you say yes, I give you what you want, right? The only way I won't start to talk about geometry is if there are any questions more on polyatomic ions. Yes, ma'am. Okay. Are you in second or third? Second? Let me go ahead and tell you what I'll do. I'll go ahead and turn off the overhead, and we'll just spend, we've got 5 minutes left, am I right? I'm not giving you what you want. I'm assisting one of your classmates. How's that? It's not just doing what Lexi wants.
Why do you chew on it?
Actually, let me kill it. It's dead. Hey, Cody, can I borrow your book? I want to use it to write the problems on the board. And Jess, what were your questions? Jessa? Sorry, I don't mean to always drop the Okay, balance the chemical equation Ba NO3 2 plus NaOH. Okay. This is going to be one of the difficulties with the two additions, and I'll tell you why. And I'll tell you why second edition you're going to have, it's going to be a lot simpler than your book shows. This is not an intended consequence, but start with that one. I'm going to share with you why some of the things in second edition now are beyond where third edition is. Remember I said just a few moments ago that there was one time in class when you saw something and it was just a whole bunch of gibberish, and now when I write it on the board, you're like, I get that. I know what that is. Okay? The difficulty you're having with this is because this in module 2, in second edition is which module? 9. In third edition, which module is it? 5. Guess what? What this is asking here hasn't happened yet in edition 3. We haven't gotten this far yet. In second edition, because they teach it in a slightly different order, you've already covered how to do this if you just did purely second edition. So last year's class, by the time we did molecular geometries and polyatomic ions, we had already talked about balancing equations. We haven't done that yet in here. That's module 6 in the third edition. Okay, so this is where we start getting into some of these difficulties. The concept of polyatomic ions and the concept of molecular geometries are the same, and the paragraphs that are in the books are the same. They're just put in a different order. So some of the questions that you're going to be asked in second edition are beyond the scope of what we've covered in this class. And that's why you can't just simply go by one or the other. What we can do this, though, let's go ahead and say, and this is a good example of why being able to figure out how many of each element are in the compounds. Let's go through the exercise. I'll go through the exercise and see if it makes sense to you. Let's look at this side of the equation. Let's look at the reactant side of the equation. What are the different elements that we have on the reactant side? Look at the elements. We have barium, right? We have nitrogen. Excuse me. We have nitrogen. We've got oxygen. What else do we have? Sodium, oxygen, hydrogen. Okay, let's count them up. How many bariums? 1. Nitrogens? See? How many nitrogens do we have? We have, over here, we have 2 of them. Every molecule has 1, and we've got 2 of them. So nitrogens have 2. Oxygens. There's 3 times 2 is 6, plus 1 is 7. How many sodiums? How many hydrogens? Okay. Now, AQ is phase symbology. It says it's aqueous. In other words, it's in a solution. It's liquid. It's dissolved. And the S means it's solid. L means liquid. G means gas. So those are 4 different phases. Now, let's look over here on the product side. This is a reactants. Now let's look at the products. How many? 1. How many nitrogens? 1. How many oxygens? We'll be done in just a moment. There's oxygen. There are 2 here, and 3 make 5. Sodiums? 1. Hydrogens? 2. See, I just want to emphasize you need to be able to tell how many there are, because the next step would be to change the superscripts in order to balance it, to have the same number of reactants as products, because you can't gain or lose any. You got to end up with the same number you started with.